All right, let's get started. So lab 1 and homework 1 will be uploaded sometime today. So I think tomorrow you're gonna do lab 1. Okay, and so the content of lab 1 will be covered today. So, but hopefully you have seen Fourier transform, Fourier series already, so it should be okay. And for lab 1, it's only simulation, so there's no hardware required for lab 1. Okay, so if you prefer, you can do that at home as well. So don't need to go to the lab. All right, so yeah, let's do a very brief review of the last lecture. So in the last lecture, so basically after introducing the decimal notation for power, and then we just went over the concept that you should learn from a system, signal system class, right? So yeah, and for decimal notation for power, you can see that. So normally we have linear unit for power, and the milliwatts equals to 1,000 times watts, right? And then, so in practice, we can use the dB notation, right? So we just use the 10 times log base 10 to compute the dB notation. And when we transfer everything to the milliwatts, then we have dBm notation, so which is equal to the dB watts plus 30. Okay, so that's a very important relationship. Just remember that. And then we have an example, and you can see the solution in class. So here's the definition of complex numbers. So for a complex number, we have a real part and the imaginary part, right? And I have two forms. One is Cartesian form, the other is polar form, okay? And both of them will be used extensively in our class. Okay, and here are some conversions and commutations, including addition, multiplication, and the conjugation, right? Just all of them are pretty important. Please remember those. And so here we have the Euler's formula. So that tells you the relationship between the complex exponential and the cosine j times sine. Okay. So by the way, who knows the proof of the Euler's formula on the top? How can we show that? Yes. Taylor series. Very good. Right. We just do Taylor series expansion on both sides, and we compare those two. We're gonna see that they're the same. Okay. Very nice. Okay, great. And so here's the definition of the inner product and norms. So this is the definition of inner product. So basically, we're going to see that we have an application of that today. Okay, and so those are for functions, and those are for vectors. All right. And then, so if we compute the inner product with itself, then we have the definition of norm. Okay. So basically, those are definition of norms, right? And those are for functions, and those are for vectors. Okay. And then, so when we say if the inner product between two functions is equal to 0, then we have the concept of orthogonal. Okay. And so those are some basics. And then we talk about the energy and the power of a signal. Okay. And the norm of a signal basically give you the energy of a signal. Okay. And if the signal is real, obviously we don't need absolute value here anymore. And when the signal is called energy signal, we need to make sure that the energy exists, right? It's less than infinity and bigger than 0. Okay. So yeah, so the energy cannot be infinity. Okay. But when the energy is infinity, then basically what we do here is that we introduce the concept of power, right? So basically, the power, definition of power is nothing but the normalized energy, right? So we compute the energy per unit time, okay? So this is the formula. So we can compute some kind of energy from minus t over 2 to t over 2. And then after this computation, we normalize it by the length, time length of t, right? And then we let t go to infinity, okay? So that's the definition of power. And when we talk about power signal, in most of the cases, so we talk about the periodic signal, right? So for periodic signal, basically it means that the signal repeats itself. Okay, and for periodic signal, then we can use another simpler formula to compute the power given by this, right? So basically here we don't have to let t go to infinity anymore, right? So here t represent the period of the signal, right? It can be any period, right? It could be the smallest period, or it could be just any period, right? We just need to compute the integral of the function square, right? And then normalize by duration of t, right? So that will give you the power, okay? And when the power is bigger than 0 and less than infinity, then we say g of t is a power signal, right? The important thing here is that the power has to be bigger than 0, right? When the power equal to 0, so it basically is an energy signal, okay? And we want to, it's a classification, right? We don't want a signal can be both energy and power, right? A signal is either energy or power or neither, okay? By the way, who can give me an example of a signal that is neither? It's not power. It's not power signal. It's not energy signal. Any idea? Yeah, signal has to be weird, right? Right. If for a kind of normal signal, it cannot be like this weird, right? So actually, we talked about this signal in our last class. The delta signal is such kind of signal. Okay. The power does not exist. It's still infinity. Okay. Yeah. Great. And when we compute the DC value, so basically we just need to compute this integral. Okay. And in your lab 1, so I think you're gonna compute some DC values. Okay. And then we talk about 3 special functions. The first special function is called complex exponential, right? It's given by this. So this has a vastly, this use in communication, right? That is one of the most important functions that we're going to see everywhere because that's the base for the Fourier transform, Fourier series, and so on, right? So that is super important. And here are some properties of the complex exponential. You can take a look. Okay, and so yeah, those are some simple formulas that we use for mathematical tricks, and so those are from Euler's formula, and the second signal that we care the most is the delta signal. Okay, so basically the definition of delta signal is that it will be 0 at anywhere else except at t equal to 0, right? So when t is 0, it will have a very big peak, right? It goes to infinity, but that infinity is a very special infinity, right? So when you do the integral of delta signal, then it will give you 1. Okay, so we have some intuitive understanding of delta signal, which are given by this, right? So basically, we can think a signal like a very big peak, right? So when the duration goes to 0, then the amplitude will go to infinity, right? But those are just the intuitive understanding of delta, right? It's not the real delta, right? Even when epsilon goes to 0, so this we usually mathematically we don't say that goes to delta signal or delta function, right? But that is an idea of delta, okay? And okay, and for the discrete time case, the definition of delta is much cleaner. So when n is 0, so instead of infinity, we just have 1. And when n is not 0, we just have 0 here, right? It's a very clean definition for the discrete time case, right? I think here for signal system, you'll learn the discrete time case first and then learn the continuous time case, right? I think the reason, it's kind of natural, right? Because I think, when I was a student or, when I teach in the University of Utah, so we learn the continuous time first and then we learn the discrete time case, right? Because normally it's easier to consider a signal, we can transfer a signal from continuous time to discrete time. We just do a sampling, right? It's kind of, natural, but the drawback of talk about the discrete time first, the continuous time first is that for the continuous time, the math is harder, right? Because we have a lot of this continuous weird stuff like the direct delta signal, right? That's a very weird signal, okay? When we first introduce to student, student may not be very easy to handle this kind of math, right? Because it's kind of weird, right? Because p goes to infinity, so why the integral still exists and it's 1, right? Kind of weird concept. So by the way, do you know why? So for the direct delta signal, so for this kind of integral equals to 1, do you know what kind of integral that is? So anybody know why? How can we have such kind of definition? Yeah, so that's from the deep math, right? So yeah, that's kind of the measure theoretic definition of a function. So that's kind of, yeah, it's not that relevant to this class, but just wondering. Okay, great. And then we have a bunch of delta, the property of a delta signal, right? We're gonna revisit it at some point, probably later this week or beginning next week. So the first is a scaling property, right? So you just remember that. And the second one is very important. So that's a multiplication property. So basically it means that any signal multiplied delta signal, and then equal to the signal at 0 multiplied delta itself, okay? Right, because everything else is 0, but at point 0, and if we do a shift on delta, then only g of t will left, right? Everything else will be 0, okay? And from this multiplication property, we can easily get this sampling property. So we're going to see the application of that today. So this is extremely, extremely important, right? So basically it means that if we do this integral, right, we do this multiplication, right? And from here you can see only g of t will be left, and everything else will be 0, right? And then we can take this out, and then the integral of delta is just 1. So basically this means that we can sample any point of a function g using delta signal, okay? So this is a mathematical operation of sampling, okay? And that is extremely important. So when we do convolution, so we're going to start from here actually. So this is extremely important. Okay, great. And then we have the definition of the unit step function or unit step signal. And so basically this signal means that when t is bigger than or equal to 0, then that's 1. And when t is less than 0, it's just 0. Okay? And we can use the integral of delta signal to get u of t, and use differentiation to get the delta from u. Okay? And yeah, those are basically what we covered in the last class. Okay, so in this class, we're gonna do the very similar stuff. So we're gonna review the important concept of signal system, right? And we'll just go over a bunch of slides. So if I go too fast, just watch the video again, and check if anything you missed or forgot. Okay, and probably in the next lecture, I'll do some more reviews, and then we're gonna see some new stuff. Okay, so and then when I see new stuff, I will use the board, not this. I know it's very fast, so, but since most of you should see that already, then I think it should be okay. And so we have 3 topics here. So basically, in the first one, we're gonna talk a little bit about the introduction of the Fourier series, and then we'll talk about a periodic signal and how the periodic signal passing through a system. Okay, and then so we're going to do the same thing for the non-periodic signal. Okay, so that's the agenda for today. All right, and so basically, yeah, the goal that we have this kind of discussion is basically to introduce you to the frequency domain. Okay, so basically, we're going to talk about this a little bit later, but so why we need such a representation of signal, right? So basically the idea is like this. So we have a signal x of t. Now we consider xt is a real signal. It's not complex. And then we're going to decompose it into this kind of thing, right? Ck is some kind of like coefficients. And then phi k is functions, right? So those functions are called bases, right? Ideally, or the idea of this is that, so we want to use the phi k to represent any x of t, right? So in this particular case, we consider phi k, each of phi k is a periodic signal, right? And then x of t is also a periodic signal, okay? So again, so we want to introduce a bunch of phi k, and the idea is to use phi k to represent any periodic signals, hopefully. Does that make sense? Yeah, of course, we cannot do that, right? But for some specific periodic signals, okay? And so since our x of t is considered to be periodic, then we assume it has a fundamental period of f0 and a fundamental period of t0. Again, so fundamental period is nothing but the smallest period, right? And the fundamental frequency is nothing but 1 over t0, right? Is that clear? Okay, great. And for phi k, so here, in particular, we're going to pick that to be cosine or sine. Okay, so that's the one that we use. And we can see it's either k 2 pi f0 t or sine k 2 pi f naught t, and f naught is the fundamental frequency of this guy, okay, the original signal, and then we just have a k in front, and k can be any integer. Right, k can be any integer, okay, and in addition, we let omega naught to be equal to 2 pi f naught. So the unit of f naught is hertz, and unit of f naught is just rad. Okay, and given this, so we can introduce a Fourier series for real signal x of t. Okay, and when x of t is real, then we can have this kind of formula. So basically, we have a constant here, and then so we have a summation over k, where k is 1 from 1 to infinity. And here we have ak multiplied cosine and bk multiplied sine. Okay. So important thing here is that so I have a k here, right? K is the variable for the summation, right? It basically means that for x of t, it only has the multiple of the fundamental frequency component. Okay. And from here we can see that so basically x of t has this many frequency component, right? It has something at omega naught, at something at 2 times omega naught, and 3 times omega naught, and so on. Okay, right? And this is called the synthesis equation. Basically means that if you know a naught, ak, and bk, if you know all of them, in addition, you need to know omega naught, right? That's very important. You need to know the frequency, the fundamental frequency of the original signal, and then you can use this equation to get back x of t. Okay, that's why it's called synthesis equation. And the formula to compute all the coefficients, a naught, ak, bk, so those are called analysis equation. Okay, so basically the analysis equation tells you for each frequency component how big that is, right? Because ak is in front of this guy and bk is in front of this guy, right? It tells you how big this frequency component is, right? So those are the Fourier series for the real signal, okay? So you have seen that before, right? Okay, great. And now the question is that, so those equations look kind of ugly, right? Because here for the same k, so I have two components. I have a cosine and sine, right? So it seems not very easy to use, right? Can we kind of combine them to have a cleaner way to write this, right? If you compare this with this formula before, so it's not exactly the same, right? So here we just have 1 phi k, and the k is from minus infinity to plus infinity, right? But here, we have something similar, but it's not identical, right? So here k is from 1 to infinity, and for each k we have two components, right? So how about we change one of this component, to minus k, right? So that can be ideal, right? So that is what we're going to do next. But before that, let me introduce the concept of the bandwidth, right? We have seen that, right? So we can decompose each signal into different frequency components. Okay, so and we can use the synthesis equation to get the original signal back using all the frequency components. Okay, this basically means that so in the frequency domain, so we have exactly the same signal, right? We have the same meaning of it, right? So instead of time, now we have another domain, so which is frequency. Okay, and from the synthesis equation or analysis equation, so we can see that. So we can see how much frequency is used by a signal, right? So because we have AK and BK, okay? And also, and another benefit for that representation is that we can get an idea of how much signal will pass through a system, okay? So normally, later on we're going to see that. So when we pass a signal through a system, so we can think this procedure in the frequency domain, right? If we know, how much frequency component we have for each signal, and then, we can see, okay, so which component can be passed through a system or not, okay? So that's basically the idea of the bandwidth, right? So normally, the bandwidth will be determined, by how much power of a signal can be passing through a system, right? If most of the power can be passed, then we say, okay, so this bandwidth could be the bandwidth of a system, right? So that's basically the idea, right? And the question is that how can we calculate, right? The bandwidth of a system basically means that how much of the signal can passing through the system. Okay. All right. And also we can talk about the same thing for the signal, right? What is the bandwidth of signal, right? Basically means that how much frequency component we have for each frequency part. All right. Okay. So yeah. So the idea is basically we need to represent a signal as a sum of the individual frequencies, as what we have done already, right? And what we did is to use some sinusoid to represent each frequency component of a system, right? And so in practice, we have two kinds of signal. So one is periodic, one is aperiodic or non-periodic, right? So basically, so for these two signals, we need to consider them separately, right? So let's see how we can do that. So the first case is that, what about a periodic system, a periodic signal, okay? And so now we use a different notation. So we let S of t to be a periodic signal under some conditions, right? So as we said, so the idea is to represent any periodic signal by using its different frequency component. But in reality, that's not going to happen, right? So actually, when the signal satisfies some conditions, and then we can do that. Otherwise, we cannot, right? So we're going to introduce the conditions a little bit later. But now we just say, OK, let's S of t be some periodic signal under some conditions. OK. And same as before, so we assume the fundamental period is T naught, but the fundamental frequency is F1, right? So basically, the reason that we do that is to indicate that here F1 basically means 1 times the fundamental frequency. OK. So instead of the real signal, x of t, we considered before, so now we assume s of t is complex. OK. So instead of sine cosine, here we consider the complex exponential, so denoted by this, right? So this is complex exponential, and we have j omega t, where omega equals to 2 pi times f1, okay? And f1 equals 1 over t naught. You can see how we can get this, and then using the Euler's formula, so the complex exponential is nothing but the cosine part plus j times the sine part, okay? And we call the nth harmonic frequency of a signal with a period of t naught is this guy, right? So basically, Fn is denoted by n multiply F1. Okay, so like the k before, right? Before we use k, so k multiplied omega naught is just multiples of the fundamental frequency, and we call that harmonics, right? The nth harmonics in this case. Okay, very good. Any questions? Yes.
To the j 2 pi t over t naught.
Why is that?
Like, why is the j still? Yeah, I understand the second level. Why is the j still inside the argument in the cosine and sine? Right.
Oh man, this is a typo. Yeah, very good question. Yeah.
Okay, I just want to make sure.
Yeah, very good. Remove it. So, yeah, it's a typo. So we don't have j there. Very good. Thank you. Any other questions? Okay, great. Okay, and so now let's, so before we have G1, right? So this one basically indicates F1, right? The first harmonic. And then, so we can generalize it to have the nth harmonic. So basically Gn is defined in this way. So basically the difference, you actually get rid of this J as well. Yeah, so just remove this J. I will revise it later, but we don't have this J here. Okay, yeah, and so Gn is nothing but just n multiply the fundamental frequency, right? So here is the nth harmonic of G. Okay, and so now given all this complex exponential, so it turns out that the G of n, all these complex exponential are the basis of this function space, okay? In other words, so we can basically decompose the original signal, S of t, which is periodic, as a summation of this guy, right? And you can see this is a series, and so this is basically our synthesis equation as before, right? Before we have all this cosine sine part, But now we can see using this, so we have only complex exponential, so which is very clean, okay? And here, so the n is our k before, so that is from minus infinity to plus infinity, right? So this form is exactly the form that we want, right? We have a coefficient here, right? Multiply a base function, right? And something like that. And so I call this inverse Fourier series, right? The reason I call it inverse is that, so basically in this case, if we know s of n and we know t naught or omega naught, and then we can get back of s of t, right? It's kind of the inverse transform, okay? Or we'll see the Fourier transform is exact like that, right? So this is basically the inverse operation or the synthesis equation. Okay, very good, right? And then the next question is how can we compute the coefficient, right? Similar to before, so basically this is the formula to compute the coefficient, and we can see what we do is that we do inner product between s and g for each n, right? And then we do some normalization, okay? And then so because we know the how we can compute the inner product, and this is basically the formula, right? And we write it down. So we have the denominator and divided by the numerator, right? And then using this formula, we could compute the Fourier coefficients, okay? So basically, this is how we can do that, right? So we have this limit thing going on, but because of the periodic property of our signal, and then so this is the final formula that we're going to use, right? Where t naught is the fundamental period. Okay, and we plug g in, and this is what we get. Okay, so this is if we know the original signal s of t, and then we use that to get the Fourier series coefficients, right? So I call that forward transform or forward Fourier series. Basically, it means that using the original signal x of t, and we can get the coefficient. Where the coefficients tells you how much for each frequency component in the signal. Okay, and that's why I call that forward Fourier series. Okay, one thing we need to notice is that, so one is basically this equation. Yeah, for this equation, so it holds when n has to go from minus infinity to plus infinity, right? So normally, we need all the component here, okay? But if we have only a few of them, right? So these two will not be equal exactly, but may look similar, okay? So this is what we want to emphasize here for this sentence. So basically, the norm of the error goes to 0 as the number of sinusoid or complex exponential goes to infinity, right? Otherwise, there will be a difference, right? So here is some experiment here, right? I say if we consider a square waveform, okay, the blue one, and then if we only consider two terms in the Fourier series, basically two terms meaning the constant term, right, or the DC term, and we just have one harmonic term, right, the first harmonic. Right, and you can see in this case it's basically a cosine, right? So, so the green one and the blue one are pretty different, right? But you can see the accent here, right? So they're pretty different, but they're related, right? And but when we have four terms, you can see the green one will be much closer to the blue one, right? And when we add more terms, so the green one will finally converge to the blue one, right? So that's basically the idea. And basically, in your lab one, you're going to do this, right? You're going to do some experiment to see, how the green one will be close to the blue one, and what are the error look like, and so on. Okay. Any questions so far? Okay, very good. And here is one example. It's a square waveform, and also that is your lab one. So, but different problem, right? So here I consider everything is above 0, right? So and for this one, let's compute the Fourier series coefficients here, okay? And from now on, we only care about the complex exponential Fourier series, right? Don't care about the cosine sine version anymore, right? Because that is not what we use in practice. So in practice, we use a complex exponential version. Okay, and so I'll skip the details. So basically, we'll just use the synthesis equation, we'll just use the analysis equation to compute S of n, right? Just to do some integral there. So do that on your own and see whether you can do it or not. So basically, that is your result, okay? And we can rewrite that in another way to get rid of the sign notation, okay? And this is what we get, okay? So that is the S of n. And if we take a closer look at it and plot it, so basically this is what the Sn look like, right? And now let's see what can we see from here. So this signal is a time domain signal, which is a periodic square wave waveform, okay? Time domain. And this one, so each of them, so represent a component in the frequency domain, okay? So in this case, so fortunately in the frequency domain, so we don't have any imaginary part, we only have a real part. Then we can just plot it in this way easily. If it's complex, we cannot do this plot, right? We have to plot the real part and the imaginary part separately, or we plot the magnitude and the phase separately, right? But in this case, it's real, so we can plot this. Okay, and remember the idea of it, right? So the idea of Fourier series is that for a periodic signal, right, and then we can kind of decompose the signal into this figure, right? And each component represent how much component we have at this frequency point, right? So here, meaning that we don't have anything at this frequency point, and here means that we have this much negative for this frequency component, and so on. Okay, and these two signals represent the same signal, right? If I draw this signal, so it represents exactly the same as this signal, but here we can imagine, so all of these coordinates are k. K means the multiples of what? Fundamental frequency, right? So basically, this can be understood as the frequency domain signal, okay? Right, so each component here represents how much we have for each frequency component. Does that make sense? And one more very interesting thing here is that we can see that the signal in the time domain is continuous time, right? And it's periodic. But in the frequency domain, this signal is exactly the opposite. So it's aperiodic, right? The signal does not repeat itself, and it's discrete, right? Because the x-axis are all k, where k are all integers, right? The signal in the time domain continuous and periodic. So in the frequency domain, it's aperiodic and discrete, right? Which is kind of interesting, right? So we're going to see many of this kind of interesting behavior later. Okay, and here is a summary. So basically, for the complex exponential Fourier series, so we have analysis equation, analysis equation, and this is the forward transform, okay? Because we get from the time domain to frequency domain. It's a forward transform. And we have the synthesis equation, so which is the inverse transform, because we can get from the frequency domain to the time domain, okay? And you can see that I'm just, compare this with the Fourier transform maybe you're more familiar with, right? So that's basically the idea. Okay, so here comes to some conditions for the existence of Fourier series. As we said, right? So we cannot do this for any signal or any function. So the function has to behave a little bit nicer to do the Fourier series, right? So those are the three conditions. The first one is pretty obvious. So basically, we need to make sure that the signal s of t is absolutely integrable, right? If the integral does not exist, then we cannot do that, right? And the second one, third one, kind of tricky. So we need to make sure that Sn have a finite number of maxima and minima in one period, right? We cannot have multiple maxima and minima, right? The third one is that, so within one period, it has to have finite number of finite discontinuous point, right? Finite number of finite discontinuous point, okay? So those conditions are sufficient, but not necessary. Okay, they're sufficient, meaning that if we have signal satisfy all of this, then we have Fourier series, okay? But they're not necessary, meaning that for some of the signal that does not satisfy this condition, they may still have Fourier series. Does that make sense? Or can you give me a counterexample that for a signal that does not satisfy one of them, but still we can compute the Fourier series? Right? How about the example that we just seen? Right? How about this example? Right? For this signal, okay, so within one period, from here to here is absolutely integrable. Good, right? And for one period, does it have finite number of maxima and minima? No, right? Because the maxima is 1. Right? We have infinite number of 1, and minima is 0. Right? It's continuous time. We have infinite number of zeros. Okay? It does not satisfy the condition number 2. So it did satisfy the condition number 3, but it does not. It violates the condition number 2, right? Which is in one period has only finite number of maxima and minima, right? And you can see, right? So those are sufficient, but may not be necessary. Okay, and then we're going to see actually so many signals can break this rule to have Fourier series. Okay, so yeah, but still, it's sufficient. Okay, so this kind of condition has a special use here, right? So when we talk about system, so we can use this kind of thing to determine a very nice condition for some systems, actually. Okay. Okay, and the other thing, which is very minor, not important, are all this paragraph. You can read it. So basically, it basically means that when we do the inverse transform, or when we do the synthesis equation, like this, okay, we cannot get exactly this back. So what we can get back is all the continuous point. Right? For the discontinuous point, we cannot get it back. Does that make sense? Which is kind of weird, right? So for example, so for this example again, right, for the continuous point, right, for all the ones here, we can get it back. But for the discontinuous point here, right, like at point 1, okay, so we cannot get it back. Why? The reason is that when we do the integral, right, the discontinuous point doesn't matter. No matter at this discontinuous point is 0 or 1 or half, the result will not change. Right? When we do a Riemann integral, all the discontinuous point doesn't matter. Right? But when we want to get it back, right, using the inverse transform, the inverse transform, we have to get some point here, right? So what does this discrete point equals to when we compute the synthesis equation? Right? Actually, it equals to half of here, right? If here's 0 and there's 1, so basically for the inverse transform, what we get is half, 1/2, right? So this is what this paragraph tells you, okay? So it's just subtle point, right? We need to be super careful. But in practice, no one cares about the discontinuous point, right? It's a mathematical artifact. Does that make sense? Okay, great. Yeah, it's not so important, but just some subtle point. Okay, so now let's talk about the main subject, right? So when a periodic signal passing through a system, right? When the input is S of t, and then the output is R of t, right? And then what is the relationship between R of t and S of t? Okay, and assume you have studied signal system. So basically, this H of t is the impulse response of a system. So did you still record this word? Impulse response, meaning that when the input is a delta signal, and then H of t is the output. So that's called the impulse response of a system. Okay, and in particular, in this class, and in many other classes, what we care about is a system so-called linear time invariant system. Okay, so we're going to take a deeper look at this. That's so important. So all the communication system, including wireline communication system, wireless communication system, so we're trying to model the system as a linear time invariant system. Okay, and this is the definition of linearity, right? So basically, meaning that if our input signal is a times x1 plus b times x2, right? And then the yt is given by this guy, right? And if the output, right, this is the input, and h is our system, right? This notation meaning that a signal passing through a system, right? If this guy equal to this guy, then we say the system is linear. Does that make sense? Right? So maybe we can have a little bit deeper look at this. So basically, let's see what does this part mean, right? So this part basically means that if the input is like this, let's say our input is x1 of t and x2 of t. Right? Can you see what I'm writing here? Okay. And then I say, first of all, so what we do is that we multiply this guy by a, and then we multiply this guy by b, right? And then together, we add them together. So this is ax1 of t plus bx2 of t, right? And then we're passing that through a system, so we denote that as h here for now, right? And then we get y of t, right? So this is what on the left-hand side mean, okay? And on the right-hand side, let's see what does that mean, right? So this basically means that, so we have a signal, x1 of t, right? And we pass that through a system first, h, right? And then we multiply this by a, right? And then we have x2 of t passing through the system again. And then we multiply this guy by b, right? And then we add them together, right? And then the output is what? Is this a multiply h of x1t plus bh x2t, right? And if we say they're equal, then we say the system is linear, right? You can see the difference here is nothing but the location of the system, right? So here is the system, and here is the system, right? Right. We can, do some operation of a signal and then passing that through a system, or we do passing through a system first and then do some operation. They are identical, right? It means, in this case, it means the system is linear. Okay. Next, time invariant. So what is time invariant of a system, right? In definition, it's given by this, right? So if we do a shifting of the input signal and then passing that through a system, and then we have an output, right? This output equal to this, and then we say the system is time invariant, right? So yeah, let's draw a figure again. Yeah, maybe I'll draw it here. So basically, yeah, those concepts are it can be very confusing, right? It looks easy, maybe natural even, but actually it is not so natural. So let's see. So let's draw this part first, right? So yt minus tau. So basically, it means that we have a signal x of t, and then we're passing through a system h, right? And here we have y of t, that's the output, and then we do a shift by tau. We do a shift by minus tau to have yt minus tau, right? So this is the right-hand side. Left-hand side, sorry, this guy, right? Let's see what is happening here. So basically, for that guy, it's nothing but, so we have an input of x of t. We do a delay first to get xt minus tau, right? And then we pass that through the system, h, to get h of xt minus tau, okay? And if we say they're the same, it basically means that the system is time invariant, right? Why it's called time invariant? It basically means that, so it doesn't matter when we're passing through the system, right? The result will be identical, right? So here, so we pass the system, same color. So here, it means that we're passing through a system first, and then we do a delay, or we do a delay first, and then passing that to a system, and then the output is identical. So meaning that the system is not changing over time. Does that make sense? Right? Yeah, those two properties are very, very non-trivial. And if a system satisfying these two properties, we call it linear time invariant system, or LTI system. Okay, very important. Okay, so yeah, so one good example to really understand, how what LTI system is to think about this example, right? Yeah, do not read this. So we have a signal, we have a system where yt equals to a times x of t plus b, right? Is the system linear or linear time invariant? Or first, when we see whether a system is LTI, we need to see a system whether it's linear first and then time invariant, right? So basically, is this system linear? So is this guy linear? Right, think about it. I'll go fast, right? Actually, in general, no, right? Because we have this b here. This constant is a troublemaker. So we call that a fine system, right? When b is 0, the system is linear. When b is not 0, the system is not linear. How to do that? Check with the definition, right? So basically, we compute. So we compute this part and we compute this part and just compare them, see whether they're the same or not. Okay, that's how we do that. Okay, yeah, I'll skip the details. So do that on your own and see whether that makes sense or not. So next, let's talk about convolution. Okay, so for convolution, so this is actually what happened when a signal input into a LTI system, right? Convolution tells you the relationship between the input and the output, okay? And we derive convolution, right? It's not just a definition, right? So when a system is LTI, so convolution is what's really happening, okay? And here is how we derive convolution. So basically, we start from this equation. And as you recall, so this is exactly the sampling property of a delta function, right? The only difference here is that we use this on the signal itself, right? We have x here, and we have x here, right? But this x is nothing but just a coefficient, right? So if you compare the formula we have seen before, so this is the sampling property of delta signal, okay? And we start from here. And so we assume h of t is the unit impulse response, which is the output of a system when the input is a delta signal, right? And now let's see how we can compute the output of a system, right? So basically, as we said, we assume the system is LTI. So this basically means that the system is time invariant, right? Again, so this is the meaning of the time invariant of system, right? The system does not change over time, right? The impulse response stays the same when we shift it. Okay, and again, so this is the linearity property. So this is the one that we introduced you before, but this is not enough to prove convolution. So we need more complex version of it, right? For example, the first step is that how about we increase 2 items to more items here? Okay, so this is an extended linearity definition. And we can even replace this sum by integral here, okay? So basically, it means that this is a signal, and if we pass that through a system, so that is equivalent to we pass the system first and then do the integral, okay? And this is the version that we're going to use to prove convolution. Again, if everything is discrete time, so that would be much easier. So it's just a messier when we consider the continuous time system, okay? All right. And so we have the definition of h of t, and then we would like to represent yt in terms of xt and h of t. Okay, so that's our goal. And the derivation is actually very simple, right? The first step is to write x of t using the sampling property of delta signal by this, right? And then from here to here, we use the linearity property, right? The linearity property basically tells you that we can move h from outside to inside. Okay, and next step is to use the time invariant property, right? Time invariant property basically means that, so this equals to that, right? Delta is the input. If we do a shift in the input, it's equivalent to say we also do a same shift in the output, okay? And this equation is exactly the convolution, or the convolution sum. Sorry, convolution integral. Okay, that makes sense, right? So this tells you the relationship between the input signal x of t and the output y of t. And this relation is done via the unit impulse response h of t. Okay, so we're almost out of time. I'll just give you a glance of it. We're going to continue in the next lecture. So now let's go back to our original idea, which is how a periodic signal will passing through a system. Okay, so it's via convolution, obviously, right? And here, so S is our periodic signal, and H is our system, right? This is the definition of the convolution. Okay, and then so we use the synthesis equation to write the Fourier series of S of t, right? So this is basically the formula, and the only difference here is that we replace t here by t minus u, so which is the convolution variable. Okay, and then we continue, right? Because now the integral is over u, so we take everything out, right? S of n is a constant, that's out, and this part is constant out, and then we exchange the order between the summation and integral, and this is what we get. Okay, so now something interesting happening. So for this guy, we have not seen this before, or you have seen this before in other classes. So this is nothing but the Fourier transform of h of t. Okay, and right, so this guy is nothing but the Fourier transform of h of t, and if you compare this and the previous term, we just need to replace f by n over t naught, and this is what we get. Okay, so this is the output of when the input is a periodic signal. Okay, and if you compare to the input, which is s of t, you can see they're almost identical. The only difference is this guy. We just have additional term of the system h here. Okay, and this h is given by its Fourier transform. Okay, so y is cut. Okay, so basically, this sentence tells you that. So when the input is a complex exponential, right? The output is nothing but the original complex exponential multiply a coefficient, so that is related to the system unit response. Okay, yeah, I'll stop here, but think about it twice. So that is actually very, very cool, because by using this relationship, knowing the channel becomes, or knowing h becomes surprisingly easy, right? We just need to, inject a complex exponential into a system, and then the output is the corresponding system multiply itself, right? So actually, the most advanced communication system, so-called OFDM, is 4G, 5G, all of them using that. It's based on this concept. That's it. Okay. Yeah, we're going to continue in the next lecture. But now it's enough for you to do lab 1. So thank you.